Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. Okay, now let's talk about section 3.4. Now in this section, we're going to talk about the scheduling of real-time processes. Now so far, we have talked about the scheduling of batch processes. Now, batch processes are mostly long-running processes. So once a process is created, it will be running for a very long time and then generate the output. Now, because of this, the scheduling algorithms for the batch process are mostly different from the scheduling algorithms of the interactive process and the real-time processes. That's something we're going to talk about in this section. So the scheduling algorithms for the batch processes are FIFO, if you still remember. First in, first out. And the shortest job first, right? And then SRT, the shortest real-time first. Now, the scheduling for the interactive process are also different. So for interactive processes, the most scheduling algorithm we're going to use is the round robin. Okay, and then the multi-level scheduling algorithm, and then you have a multiple priority levels, and at each priority levels we're going to use the round robin, and then also the multi-level feedback scheduling. Now, the switches between the interactive processes are very frequent. So using the round robin, typically a process is going to actually run for like a couple of some milliseconds or even microseconds, and then switch to the next process. So that's why interactive processes are actually running very fast, and then switch back and forth at a very fast speed. Now, the scheduling for the real-time process are different. Scheduling algorithms for real-time process are different from the batch process and the interactive process. Now, a real-time process is characterized by continual input, and which must be processed fast enough to generate a nearly instantaneous output. Okay, so each arriving input item is subject to a deadline. So, for example, here the streaming of audio and video. So, for example, if you try to, do some kind of communications like making video conferences, so then once a party generate a video stream, the video actor files, then the video should be delivered to the destination within a certain time period. Otherwise, the video conference fails. Now, the other example is like some of the systems in the autopilot, system. So in that case, once some kind of command signal is sent to the, a vehicle, and then you have to stop the vehicle within certain period of time. So these are real-time processes. Now, one of the important factor or parameter for the real-time process is called a period. So a period is a time interval, typically in a milliseconds or even microseconds, within which each input item must be processed. It's a very time critical, like autopilot program, video stream, and some kind of system in a nuclear power plant, right? Now, all these processes are very important, and the process has to be, processed within certain time period. That's a real-time processes. So one of the scheduling algorithms for the real-time processes is called RM scheduling algorithm, the rate monotonic algorithm. So the RM algorithm schedules the process according to the period. Okay. Now the priority gives to the process with short period. So that means the shorter the period, the higher the priority. Now, in this example, let's see, we have two processes. Okay. Now, the two periodic processes, P1 and P2, with given period, process 1 has period 4 and the process 2 has period 5. So using the RM scheduling, the P1 always has the higher priority than P2 because the period is 4, which is smaller than 5. Okay. So now P1 has what does that mean? So P1 has period 4, which means the first computation of length 1 for the CPU, the total CPU, which is 1, the first computation of length 1 has to be completed within time 0 and 4. So that means because the period 4, so for the P1, the first period is 4. Okay, so for this first period, the CPU, total CPU time, first actually the computation of length 1 has to be done before time 4. And then the second one has to be done before 8. So that's a period, right? Which is 4. And the third one is 12. So if P1 is the only process running, so let's say once it's started, it will immediately get the CPU and complete it. So which is fine. And then once in the second period, once it started, it's completed, right? That's not a problem if P1 is the only process running. Now, if P2 is the only process running, so the first, computation, the computation of length 3 has to be done between 0 and 5. So now the length of computation is 3, right? Because that's a total CPU then. And then from 0 to 10, so the second computation of length 3 is going to be completed in between 5 and 10. Okay. And then so on. If we continue 10 to 15, then length of 3. So that's the first period, that's the second period, that's the third period, right? Okay, now if actually P1 and P2 are running concurrently, so that means the operating system support multi-programming. Now both P1 and P2 are real-time processes. Now what happens? Okay, let's take a look. So suppose here's P1 and P2. Okay, let me change the color so we can make it easier to look at this. Okay, so P1, once it's started, the first period, is 4. So once P1 started, the computation first, the length 1 is done over here. Okay. Now P2, the period is 5. Now, if both P1 and P2 are fighting for the CPU, P1 will get the CPU because the period for P1 is 4, which is shorter than the period of P2, which is 5. So P2 can start only after when P1 complete its job, and then P2 can start from time 1 to time 4 because the total time period CPU time is 3. Okay. And then for the next period from 4 to 8, P1 will start. And then the next period from 5 to 10 for P2. P2 start at the 5 because you have to wait until P1 is complete the job for that time, for the CPU time. Okay, so here. And then comes the next period from 8 to 12. P1 gets a CPU and complete. So everything is perfect because P1 each, length of, the computation of length for each period, then P1 actually completed within the, within the time period, right? Which is within 4. So then here, the next period for P2 is start from 10 to 15. So now P2 next period start at 10. So at this moment, P1 is not running, right? P1 just done its CPU time during that time period. So P2 gonna start immediately after it start. Now, once P2 running at this moment, now for P1, the next time period start, right? Next period start from 12 to 16. And then because P1 has a high priority, so it will immediately get the CPU. So even though for this computation of length 3, P1 only just completed 2 time unit, right? So it's not done yet, but it's kicked out by the scheduling algorithm because P1 has higher priority. Now once P1 is done, then scheduling algorithm is going to switch the CPU to P2. So P2 going to continue to finish the remaining part. Now that's the scheduling for the real-time process. That's the RM scheduling for the real-time algorithm. Make sure P1 always gets a high priority if the period for P1 is smaller than P2. Now, another scheduling algorithm for real-time processes is called EDF scheduling algorithm. EDF stands for the earliest deadline first. So the EDF algorithm schedules the processes according to the shortest remaining time until the deadline. The remaining time to the deadline. The shorter the remaining time, the higher the priority. Now EDF is preemptive, which means so the scheduling algorithm can remove the processes which is currently running in the CPU and schedule the other process. Now let's take a look at each of the case. Again, we're going to use the same processes, P1 and P2. Process 1 has a period of 4, process 2 has a period of 5. Now the total CPU for P1 is 1 for each computation, and then for each computation, P2 is 3. Okay. Now, suppose both process 1 and process 2 try to compete for CPU. Now, process 1 has period of 4, process 2 has period of 5, right? Now, in this case, both process hasn't started yet, right? So now the deadline for P1 is 4, for P2 is 5. So P1 has higher priority because the earliest deadline first. So P1 gonna run for 1 time units. That's the computation of, length 1, the one, and then P2 gets a CPU and run for 3 time period, right? Okay. And then at this moment, the second period for P1 started. Okay, and the P1 is the only one request for CPU. So P1 gets a CPU and it's complete. And at this time, P2 started. The second period for P2 is just started, right? And also, P2 is the only process requesting for CPU because P1 is still in this second period. And the second period is already done. Okay, so P2 gets a CPU and run at this moment. Okay, and then the next period for P1 start. The deadline is 12. And then this is the only process. P1 is the only process, right? So P1 starts. And then at this time, the third period for P2 starts, which is actually from 10 to 15. Okay, so now at this moment, P2 is the only one requested for CPU, so P2 start. And then run at the time 12. So a new period start for P1. This going to be from 12 to 16. Now in this case, P1 start to request for CPU, right? Because that's the beginning of the new period. And P2 still in the third period, but hasn't done its job yet, because each actually CPU time is 3. P2 only completed 2, so there's 1 remaining. So in this case, P2 is already in the CPU, and the P1 start to request for CPU, right? At the time 12. Now the scheduling algorithm gonna actually check who gonna actually continue to use the CPU, or who gonna use the CPU, or whether P1 gonna use the CPU or P2 continue to use the CPU. Okay, so then the algorithm gonna check, who gets the priority. Now the EDF basically check the deadline, right? And it finds out that the deadline for P2 is 15, the current period. The deadline for the current period is 15. Now deadline for this new period for P1 is 16. So this is earlier, right? So P2 continue to run. After finish, then P1 start to run. Okay. Now you don't see much difference at the beginning, but after time 12, you see that the EDF gonna continue to grant the P2 the CPU, and then until P2 finishes, then P1 start the period. Now both actually eventually gonna be running happily because everyone actually complete the computations before the deadline. That's the most important thing for the real-time processes, right? So let's analyze the performance of the real-time scheduling algorithms. Now let's compare both the RM and the EDF. So now real-time processes basically focus more on the deadlines. So the most important goal of the scheduling algorithm is to meet all the deadlines. Okay, a schedule is feasible if deadlines of all processes can be met. So that's a priority. Okay, now we define a fraction of CPU time by Ti divided by Di. Now Ti is the total CPU time and Di is the period of a process I. So that's for each process. Now the CPU utilization is the sum of all these I. So I basically from 1, 2, all the way to n. Okay, suppose we have n processes. Now the ideal case is U equals 1. Okay, you meet the requirements, and also the CPU utilization is 100%. That's the ideal case. So that means the CPU is not wasted. Now, a feasible schedule exists as long as U less than or equal to 1. Okay. Now, if U is greater than 1, that means then the schedule is not feasible. Okay. Since the total CPU time of all processes would exist 100%. So some of the process is going to fail, definitely. Now, EDF is an optimal algorithm in that the feasible schedule is always guaranteed as long as U is less than or equal to 1. Okay. If the CPU utilization is less than 100%, then EDF, is up, there's always a feasible schedule. Now IM is not guaranteed, but now based on statisticals, that the empirical evidence shows that the RM is likely to produce a feasible schedule if U is less than approximately 0.7. Okay. So now let's take a look at the other example of the RM and the EDF. Okay, let's look at another example. Now in this case, we have two processes, P1 and P2. Now process P1 has a period of 8, process P2 has a period of 10, and the process 1 has total CPU times 3, and the process 2 has total CPU times 6. So now let's use this example to analyze both the RM and the EDF. In the previous slide, we mentioned that the EDF is optimal. Okay, so then let's take a look. So for, let's say, both RM and the EDF, now both process start the request for CPU. Now that's P1, P2, P1, P2. Now the first process has a period of 8, and the second process has period 10, right? Now for RM, P1 has the high priority because P1 has period 8, which is smaller than P2. So P1 has high priority. So when P1 requests for it, P1 get the CPU, and P1 start to run do the computation of length 8, the total of CPU. Length 3, I'm sorry, not 8. So P1 gonna run for 3 time period. And then, once P1 is done for the first period, and P2 waited for the CPU time and it gets the CPU at the time 3, right? And it runs for, okay, it will continue to run until at the time 8. Okay. Then at this time, because P1 enters the second period. Okay. So then, because P2 just run from time 3 to time 8, it just run for 3 to 8 is not 5 actually time unit. But P2 has a total CPU time 6, so there's still 1 time unit remaining. But because P1 start a new period, so P1 is also requesting for CPU time, so the scheduling algorithm is going to decide which one gets a CPU. And P1 gets a CPU because P1 has a higher priority, because the period for P1 is smaller. Now, once P1 complete the 3 time unit, then P2 should start. Okay. Now what's the problem? Now at this time, P2 already passed the first period and it hasn't completed the first period. So P2 failed. Okay. You see the point here? P2 failed. Because P2 at the time 8, P2 hasn't completed the task in period 1, but have to give away to P1, so P1 can start. Once P1 complete, P2 already missed the deadline. Okay, so that's IM. So in this case, IM can complete P1 but fail to P2. Now let's take a look at the EDF. So both P1 and P2 request for CPU, and again, P1 will get this CPU. P1 will start to run. Why? Because P1 has the earlier deadline, right? So when P1 complete job, P2 start. And run at the time 8, the second period for P1 start. Okay, now the operating system scheduling algorithm, the EDF scheduling algorithm, is going to decide which process going to run and which process is going to get the CPU. So P2 has 1 time unit left because P2 has completed the 5 time unit, but P2 need 6, so there's 1 left. And P1 has 3 time units because that's a new period for P1. Now, who will get the CPU? Now P2 is still in this period, so the deadline is 10. Now P2 is a new period, the deadline is 16. So based on the EDF, the earlier deadline first, so P2 continue to run for 1 time period. And then at this time, P2 quit the, complete, and the P1 start to run the job. So in this case, both P1 and the P2 get a chance to continue to run. And then in the second time period from 10 to it's all the way going to be all the way to 20, right? So then P2, P2 entered here. So P1 gonna basically at this moment, you know, the scheduling algorithm is going to check whether I'm going to switch to P2 because P2 start a new period. But P2, the deadline for the new period is 20, which is actually, you know, later than 16. So P1 going to continue to execute, and then P2 start, right? That's the EDF. So EDF definitely is better than RM. Now section 3.5 is combined approaches. We'll skip the 3.5 for this class at this moment. So I may add this section later on, okay? But we'll skip at this moment. Thank you.